Hello everyone, welcome back to Linked Frequency. This is the tutorial for 3.3 volt DC buck boost converter circuit design by using a TPS650230 IC. This is the Texas Instruments buck boost converter IC, which looks like this here, and this tutorial is going to design a 3.3 volt buck boost converter using that IC. This is the 18th tutorial of practice project for PCB designers, and I am Vaibhav Sugandhi, passionate PCB designer and technology startup founder. This tutorial is being a little more advanced than the previous one because in our previous tutorial we discussed about how to create a buck converter by using a separate IC which is available in industry for 5 volt design. However, in this tutorial we are going to design a buck boost converter, which means the single IC is responsible for boosting the voltage as well as buck the voltage or reduce the voltage. This kind of circuits are more often used in IoT devices where the battery voltage fluctuates between 4.2 volt to 3.2 volt or maybe a 3 volt in most of the cases. When we want a 3.3 volt constant DC at the output side, whenever we have a battery voltage of more than 3.3 volt, then buck converter is essentially working inside. Whenever the battery voltage goes below 3 volt or 3.3 volt, then obviously we need a boost converter. That's why in a single IC, most of the IoT devices will use buck boost converter with an energy efficiency of more than 80% so that they can operate with a single battery for a long period of time. That is how most of the IoT devices, especially our smartwatches and earbuds and most of the IoT products which we use with a battery operated and a long life battery design are designed inside with these kind of a buck boost converter. And now in industry, these kind of a evolution boards or the development kits are available for such kind of a buck boost converter IC for the experiment purpose, but they are extremely costly, like somewhere around 2,500 rupees for this development board, which is not at all suitable for any kind of a development activity or maybe prototyping activity with a low budget IoT devices. In this tutorial, I'm going to show you how to design this SMD component and use this SMD component to design a 3.3 volt buck boost converter. By the way, this particular IC looks so weird, SMD component it is, and some pins are so long, some pins are so short, and 3 pins on the top side, 4 pins on the other side. This looks very weird at the first glance for those who don't deal with such kind of a SMD components in regular basis. But for us, this is the one of the most amazing and most highly used component in our company at this point of time, because most of our products work with the 3.3 volt power supply and most of our microcontrollers and the development boards are dealing with 3.3 volt with a 1 ampere of a current rating or 1.5 ampere of a current rating at a maximum load condition. In that case, this IC works like a charm to us. That's why I am bringing you this advanced tutorial, which is not easy for everyone. I totally understand, but trust me, once you start understanding such kind of a design, you are most likely eligible for advanced level PCB designing roles in industry. That's why I'm bringing this tutorial for 18th level or 18th tutorial of a practice project for PCB design. Without further ado, let's start with the datasheet analysis. As I already said in previous tutorial, I'm not going to do the black box analysis and white box analysis, directly jumping onto the datasheet level of this particular IC. So when we go to the datasheet, make sure that you refer the datasheet from the original manufacturer, that is Texas Instruments, for this particular IC. TPS630250 and 251, 252 are the 3 varieties of ICs available for this particular application only. Maybe this 012 indicates something which we will figure it out through after going through this particular data sheet if you want to figure it out. But right now I'm focusing on the 250, and it is 2.3 volt to 5.5 volt input voltage range, ideal for single cell IoT devices, because each cell in lithium ion technology or lithium polymer technology, you can see that actually the cell voltage ranges from 3 volt to 4.2 volt, and it is absolutely ideal for this IC. And it has a 2 ampere of a continuous current output when the input voltage is ranging between 2.5 volt or greater than 2.5 volt, you can say. Obviously our lithium ion cell will be having a 3 volt as the cut-on voltage for the BMS inside. Because of that, we can expect a 2 ampere of a current rating provided our battery is capable of delivering 2 ampere. Output voltage is 3.3 volt constant, and if you want, you can use the adjustable output voltage as well. But right now I'm going with a fixed output voltage. Like this, the efficiency of buck boost mode is up to 97%. Extremely efficient actually. When input voltage is equal to output voltage, the efficiency is approximately 95 to 97%. So this one is, I think, you can treat it like an ideal component for the most of the IoT devices which works on the 3.3 volt. Again, it's my personal opinion. Most of the industry people may choose the other component because of cost factor or because of form factor, because of various reasons. I appreciate that. There is no question about it. But right now, for me, this one is absolutely amazing one because of its efficiency and output current and operating voltage range. And if you go through all these information, you will get to know how beautiful this product is and where all it can be used. In cellular phones, smartphones, most of the old day smartphones are using these kind of ICs only. Nowadays, they uses the different one, much more advanced one. But this one is used in most of the earlier device development and all that thing. Tablets, PCs, smartphone accessories, and point to load regulations and battery powered application. That is what I told, right? Battery operated devices, portable devices. This is one of the most used IC in the such kind of application. And if you look at the efficiency and output current graph, you can notice that 95 to 97% of efficiency when input voltage is equal to output voltage, we can achieve that. And typically it will range from 90 to 95%, which is absolutely amazing in case of IoT devices. This is the typical application circuit. Looks very simple. Only 3 to 4 external component and we are done with that. Extremely minimum circuit design at the designer level, but it does the work like a charm. And it is form factor is also much better as per my knowledge. VQFN IC it is 2.5 mm by 3 mm, which is absolutely suitable for IoT application. And if you go a little bit down, you can see a BGA package is also available and also a QFN package is also available. Most of the time we go with the QFN package because BGA package is suitable for multi-layer design, like 4 layer or maybe 6 layer PCB design. On that time, when you are designing a 4 layer PCB or 6 layer PCB, then BGA package makes a lot of sense. In fact, BGA package is even more smaller than the VQFN package. You can see here 1.766 mm by 2 mm, which is almost like maybe a grain of a wheat, you can say, a wheat size, wheat grains size actually. Okay, and if you come to VQFN package, this is how the package looks like. And you can see the functionality of each and every pin or pinouts are given in this, and you can read about it and you can understand about it. If I scroll a little bit down, or if I use this particular application and implementation, this is what we want actually. Typical application 2.5 volt to 5.5 volt and input capacitor of 10 microfarad, L1 inductor with a 1 microhenry, and you can see this one is a feedback resistor network. This feedback resistor network gives the feedback voltage to this IC so that it can adjust the output voltage. In fact, you can see here this particular resistor network is set to 3.3 volt to 2 ampere, up to 2 ampere. If you want to increase the output voltage or decrease the output voltage, as we said, it is an adjustable regulator IC also. Because of that, you can vary the resistance value here and you can literally set it to whatever voltage you want. And you also have option for PFM mode and a PWM mode. Most of the time I go with a PWM mode only, not PFM mode. But again, it is depends on what type of IC you are using and what type of a configuration you want. You have to read the entire design requirements and the design application information and then decide on that. Now I'll go to inductor. If you go here, manufacturer number is already given here. Coilcraft manufacturer number for 1 microhenry inductor, which is absolutely amazing for us to design at this point of time. So let's consider this one and let's jump into the easyEDA and start designing this one. First thing is I'll go to file and create a new project and let's start designing this one. All right, now you can see that this entire circuit is ready. In fact, the most important part is the entire circuit looks very simple with respect to datasheet, as well as here also it is very simple. First thing is I have connected these single pin connector at the input side, V in plus and V in minus, or plus V in plus minus V in, so that we can place them however we want, as we did for the 5V buck converter previous design, the 17th tutorial, right? And then we have a input V in pins and enable pin and V in enable, analog V in here. All these things has to be connected to the V in as per the schematic, typical application schematic. And inductor has to be connected here, and that inductor part number is already given in the data sheet. So I just copied it and searched for that particular component in the global library. We got it and we placed it. Thereafter, output has to be given with the feedback resistor, and feedback pin is connected to the feedback divider network. And then we have connected this 0 ohm resistor here. What is the importance of these two 0 ohm resistors? As it is mentioned in our data sheet, V in or ground. If it is connected to V in, it will work in the PFM mode, and if it is connected to ground, it will work in a PWM mode. Based on the requirement, based on the analysis, based on thorough understanding of the behavior of the IC, which one is suitable for our application, we can short those two resistors, any one of them, not both of them. You can short either R3 or you can short either R4 based on your requirement. If you short it R3, then it will be connected to V in and it works in PFM mode, and this one should be kept open. If you short both of them, then V in and ground will be short circuit. So any one of them you can short it. That's how these 0 ohm resistors are used in industry, especially in PCB designing, especially in prototyping actually. And then we have a 22 microfarad 6.3 volt capacitor, two of them. Instead of using a 47 microfarad one capacitor, a bulk capacitor, I'm using a 222 microfarad capacitor. It's a personal choice, just for our sake of convenient, I have done that. If you want, you can go with the 47 microfarad 6.3 volt single capacitor also. And then I have added a small LED here just to indicate whether the output power is coming or not coming. This is going to be a one compact module, just like how we did in a previous tutorial. Let's get started with the PCB designing. All right, here is something that I wanted to share with you. First thing is, when you see this IC, a tiny little IC which does the entire magic, you can see that it is even more smaller than the O603 capacitor. Those who understand what is O603 capacitor, they will get to know what this important thought is all about. But if you don't know what is O603, then just don't worry. You will learn it over the period of time if you continue your career in PCB design industry. So once you understand what is O603 component, then you can see in comparison to O603 capacitor, this is how the IC looks like. And in comparison to this inductor, probably half of this inductor, the IC size is actually. And if you compare it with the pin of one jumper wire, you can compare it with that particular thing. So somehow you can understand the very minute structure of this IC. Now important thing is, I don't need such a big PCB for this particular application. That's why what I'm trying to do is, I'm trying to place these components as compact as possible, but these designators are not allowing me to keep them closely each other. So what we can do is, when you go for such kind of a small minute design, you can reduce the size of these designators. How we can do that? Select any one designator, right click on it and click on the find similar object. It works with the through hole component. It works with pretty much anything in the entire PCB industry for this particular EDA tool. In other EDA tool also it works, but the option may be different. What I'm trying to do is I'm going to select the layer, not any layer. I want on the same layer, which is on top side, and then I want any text we want. We don't want only C3. We want all the text like U1, C1, J2, all should be selected at this point of time. And then line width, I will make it as the same. Height, I will make it as the same, and then I'll click on this find. When I click on that, you can see that all these designators are selected by default. Otherwise, what I need to do is, if I'm not using this kind of a trick, then I have to hold the control key on my keyboard and select each and every designator independently, which is very tiresome activity when you are designing a real-time project, and that too when you're designing in a large scale, like multiple circuits together and all that thing. Right now, what I'm going to do is, I'm going to change the line width by 0.1 and height by 1 or maybe 0.075. This is what we do in most of our applications. So this one looks good to me. Let me try with 0.125. Yeah, 0.125 looks good to me. A line width and the height will be 0.75. First thing is, I'll arrange these components once again a little bit closely so that we can handle them easily. So first thing, I'll keep the inductor on the very border side and keep a L1 like that. And I will select all of these components, and I hope this is ignored, and these two components, and move them with the arrow key on my keyboard. I'll just move them manually however I want them. So I think pretty much at the good place. Yes, here it is. Kind of a good one. So I'll just take this one here, and U1 should be placed somewhere here so that we can indicate this is the first pin of the IC, something like that. And then C1 is here. I'll arrange the C1 properly, and R3, R4, I can bring them this side. So that's how I can manage the designators. Now the point is, I'll just keep these two components a little bit close to the IC, and then I will arrange R2 at the bottom side, R1 on the top side, and these two capacitor, let me place them a little bit closer to the resistor divider network and their designator. Now I think we have this R5. I will place it here. You can notice that I'm placing them exactly straight to this, so that routing time will not be much larger to me, or it's easy for me to route the component, something like that. So I'll place this LED somewhere here so that it's easy for me to observe whether this part of the circuit is working or not working, all that thing. Okay, I hope we have got some space for our the connector here. No, actually we need to connect it like this, so I'll just reorder these things. Let me place this resistor somewhere here like this, and I will arrange R5 on the top side, and L1 probably I'll place it like this. This one looks good to me. Maybe I think let's place LED 1 on the top side, because all designators should be visible in one direction. So I'll just rearrange this one back. Okay, now let's do it in a fast forward way. Alright, now you can see that how the placement of this entire PCB is done. This is really wonderful. This is totally amazing as per my knowledge. Why? Because you can see that this entire PCB is just 20 mm by 15 mm. I think we can sell this as a module once we manufacture this if it is needed for us. So however, we can place designators here, or maybe a text information on the top silk layer here indicating this is output and this is input, and maybe we can place some detail about this particular product in this particular area. That's how I'm done with the placement of these components. Now let's start with the routing activity. All right, after a long design activity and a lot of new things in this particular advanced PCB designing technique or a tutorial, we are completely done with this particular project. You can see here I have created a solid region for input voltage. You can literally see that this particular solid region is not a ground actually. It is not a copper pore for the ground. It is a copper pore for the specific pin or a specific signal in the entire PCB. This is called solid region. You can see here solid region. By using that, you can draw that particular diagram to cover all the pins in that particular circuit to be connected with the solid copper region. Similarly, I did it for the output 3.3 volt as well, and after that I have done the copper pouring for the ground as well as for VCC. Then after that I have created the add wires or add or remove wires option. When I click on that, it will ask for the option. I have given the smallest spacing possible, that is 1.27 mm. Because of that, you can see a lot of wires here connected to this particular circuit. One small problem in this entire design activity is this IC has got only one wire through which it connects to the ground actually, which is not sufficient as per my knowledge, as per my experience in PCB designing. However, we can add multiple wires here, but it is not at all recommended adding a wires beneath this inductor, because wires can act like a inductive devices and it will malfunction the entire behavior of this inductor, or maybe inductor may malfunction because of these ground wires. That's why it is not recommended to add a wires inside this. However, I'll not address that issue at this point of time. We'll discuss about it in the later stage, or maybe we'll solve it whenever we go for the production of such kind of a product. Right now you can see that this is how the entire schematic PCB layout looks like. Top side also and bottom side also, we need a bottom copper because we want a ground stability. And then if you go for the photo view, this is how it looks like. Cute little one PCB. Obviously it's cute for me because as a PCB designer, I'm very happy for this kind of ICs available in industry, because they make our work so easy and so powerful. You can see that the 1.6 mm regular PCB looks like a very big thick block of PCB in front of this entire tiny circuit. I believe these kind of things will be fabricated with a 0.8 mm thickness of PCB. Then it looks proper to us actually. So this is how the PCB looks in 3D model, and this is how it looks in the 2D, and this is what the exact circuit looks like in PCB designing. I hope you enjoyed and understood the entire concept of this buck boost converter IC or the buck boost converter circuit design for 3.3 volt regulator. I believe that you understood and you will try by yourself. If you get any questions or clarification is needed for your design activity, feel free to comment your question in the comment section. I try to answer them as early as possible from my side. Thank you so much for watching this video, guys. See you again in the next video. Until then, like this video and share it with someone who may need it, and consider subscribing to our channel Linked Frequency. See you again in the next video. Tune yourself to make a difference.